Good morning, everyone. Can you just please let me know if you can hear me? Just by giving me a thumbs up. If you can hear me both on YouTube or just the Teams. Okay, thank you. Simlindile. I also heard Smagaliso's microphone. Okay, thank you guys. Now, first of all, thank you for joining on your public holiday. Of course, this will all be recorded. It reminds me I should record all of this. All the YouTube part is already automatically recorded. I'm just going to record the Teams meeting as well. The reason why I'm holding this session today is because I have to be traveling for a funeral on Friday when it's actually my time to present this session. Okay, so I am going to record this. This is not compulsory, but I am happy that you guys have joined. It should not be longer than say 45 minutes. Then we'll be done. Okay. I'm going to start recording now. Okay. Okay, so you can come back to this recording and then watch everything I did. Okay. Now I'm just going to have to wait like 3 more minutes. Just let me know that when okay, I'm still transcribing as well. It's just, by the way, it shows that I'm Arnold. My name is Lucian, and it seems even the dictation software of this transcript program of Teams is spelling my name wrong. But yeah, my name is Lucian Pullen, and I'm currently doing my master's here. But most of you already who've joined Teams before will know that. Okay, so let's just get that out of the way in the interest of wasting time. Okay, so let's start. Okay, I think we can start. There's about 2 minutes left. Okay, so what you need to know, just let me know. Can you guys see the screen on Teams very clearly, like the screen that I'm showing here? Okay. I know most of you are on Teams and probably only one. Okay, Mr. Caesar says you can see it very clearly. Okay, thank you. Okay, so what you need to know for this session is this formula. Okay, we'll mostly be doing something called, let me just check there. Okay, the time is, I timestamp everything by the way, guys. So the video, when you go to YouTube and you want to watch it there, and you just want to watch a specific problem, there is a timestamp there, so you just go to the problem automatically. Okay. In this case, I'm going to start with problem number 24, and all of these problems will be on electric flux. Okay, electric flux. Now you can picture electric flux as the amount of the electric field that goes through a certain area. Okay, let's say this is the area. Okay, we are dealing with electric flux. All of our questions today will have to deal with this phenomenon of electric flux. It's the amount of an electric field that goes through a certain area. Okay. Now, mostly today, and I think in general, we'll only be using these uniform electric fields. Okay, meaning these parallel lines never cross. Like a normal electric field, these parallel lines never cross. They go in and go out. They're never ending, stuff like that. They're always parallel. That's very important. Okay, so we're mostly dealing with uniform electric fields. Okay, now flux is the amount of an electric field that goes through a certain area. Okay, so it's the amount of an electric field that goes through a certain area. You can picture it as a tap. Okay, the amount of water that goes in. Well, let's say you have a tap here. Okay, there's a terrible tap that I'm going to draw here. Let's say there's a tap. Okay, this is how I used to, and there we have a round ring just beneath the tap. Okay, the flux in this case is the amount of water from the tap that goes through the inside of that ring. Okay, now that is basically what flux is. It's the amount of the electric field that goes through a certain area. Okay, so that is flux. Okay, so that is what we'll be doing today. Now, how do we calculate the electric flux? Okay, now this is the formula that you should know for today. Okay, electric flux, this is the symbol for electric flux, is equal to the enclosed charge, meaning the charge enclosed by your area, the amount of charge enclosed by that area, divided by sigma naught. Okay, and we know this, oh, by the way, not enclosed, that is enclosed charge, the charge enclosed by the area, the enclosed charge divided by sigma naught. Okay, where this is the electric flux. You can write this down if you want, you don't need to, but we'll be using this the entire session. That is the electric flux, and then sigma naught is just equal to 8,85 times 10 to the negative 12. Okay, that is numerical value. Okay, that is all you need to know about electric flux at this stage. Later on, you will learn more when you're dealing with Gauss's law, but that's what you need to know for now. Okay, let's start. Question number 24. Question 24. Okay, the question says we have two charges of 15 picometers and negative 40 picometers, and they are inside a cube with sides that are 0.4 meters in length. Determine the net electric flux through the surface of the cube. So determine the net electric flux through the surface of the cube. When they talk about electric flux, this is the formula you use. Okay, electric flux is equal to the charge Q that is enclosed divided by sigma naught. Okay, now what charge is enclosed by the surface? Okay, remember the surface is a cube. Okay, you think of normally of a cube as a volume, right? But this volume, we are talking about a cube, not as a volume, but a cube surface covering. Okay, so there's a cubic surface covering these two charges. Okay, so the form of the charge is not very important at this point. The amount of charge inside that surface is important. Okay, now the charge enclosed, they say two charges, 15 pico, so it means 15 times 10 to the negative 12 plus negative 40 pico plus negative 40 times 10 to the negative 12 coulomb. That's coulomb, and that's coulomb as well, is enclosed, and then divided by 8,85 times 10 to the negative 12. And that gives us, if you add it up at the top, it will give you 15 minus 40 is negative 25 pico, negative 25 pico, divided by 8,85 times 10 to the negative 12. Oh, that's negative 12, sorry, not negative 25, negative 12. Okay. Now please stop me at any point like there. I just made a quick mistake there, and that is coulomb. And then, of course, the units for sigma, you can just look it up, or you can just work it out. In this case, the answer should be Newton meters squared per coulomb. So you can just then work it out. Okay, so if you divide 25 times 10 to the negative 12 by 8,85 times 10 to the negative 12, minus 10 to the negative 12 minus 12 was going to give you 0. So it's just going to be some numerical number 2,82 in this case, Newton. And by the way, this is very important, flux is measured in Newton meters squared per coulomb. Okay, that is the units of flux, Newton meter squared per coulomb. Okay, does everyone understand that question? Okay, more or less get how to get to that answer. Can you just, by a show of hands, if you guys understood how to get to that answer? It is very simple. All you have to do is to just take, okay, Mr. Cole Schultz, I have heard both of those pronunciations of that particular surname, Mr. Schultz or Schultz. He says he understands. Anyone else? Everyone with me? Okay, it's just simply the charge that is inside the surface. Okay, the amount of charge going in that surface or inside, enclosed by that surface, and that is divided by sigma naught, which is always given as 8,85 times 10 to the negative 12. Okay, now the next one, let's continue. Like I said, this will be fast, guys. It will probably just take us 45 minutes. Okay, that's 25. We got an answer of negative 2,82. Let's see, negative 2,8 is the closest one here. Let's check. Yes, and we got it correct. Okay, now, question 25. Okay, it says, question 25. The total electric flux through a closed cylindrical length. Okay, so we have a closed cylinder, okay, and they say the total flux through that cylindrical length, and then they give us the length and the diameter is equal to negative 0.5 Newton meter squared per coulomb. Okay, so we are given the electric flux. We are given the electric flux is negative 5 Newton meter squared per coulomb, and they want us to determine the net charge in that cylinder. Okay, so the net charge in the cylinder. Okay, they want the Q enclosed. They want Q enclosed. Now we know the electric flux is equal to the charge enclosed divided by sigma naught. Okay, now if you want the charge enclosed, we multiply sigma naught by the electric flux. And if we do that, sigma naught is equal to negative 5.0 Newton meter squared per coulomb multiplied by sigma naught 8,85 times 10 to the negative 12. And that's going to give us, sorry, I just need to erase this, okay. We are given that the electric flux is equal to negative 5 Newton meter squared per coulomb, okay. And we want the enclosed charge, okay. Now we know that electric flux is equal to the enclosed charge divided by sigma naught, okay. Now if you want the enclosed charge, we get rid of sigma naught here by multiplying on both sides. Therefore, the enclosed charge is then equal to the electric flux multiplied by sigma naught, which is just negative 5 multiplied by 8,85 times 10 to the negative 12. Okay, and that gives us an answer of, if I work it out correctly, it should be negative 4.4 times 10 to the negative 11. Now you can write this as follows. You can just write it as negative 44 times 10 to the negative 12, or negative 44, anything that is coulomb, by the way, anything written like this should be equal to anything times 10 to the negative 12 is just pico coulomb. Okay, so that is just negative 44 pico coulomb. Okay, by a show of hands, Does everyone understand that question? It is just making something the subject of the formula. Nothing really is being tested there. You just had to see, we just had to look if something. Okay, quite a few of you got that. Okay. Oh, someone has a question. Bali, Miss Bali, you have a question? You can switch off your mic and then talk if you have a question. I see your hand is raised, or is it raised, or are you just saying that you understand the question?
No, sir, I understand the question.
Okay, thanks. Okay, so that is question number 25. You see, electric flux questions at the beginning are very easy. It's just the enclosed charge divided by the sigma naught. Okay, now let's go to question number 26. Okay, question 26 says the following. Let me just take a timestamp here. Okay, question 26 says charges Q, small q, and big Q are placed on the x-axis. Okay, so we have two charges. Okay, let's say question 26. Okay, we have question 26. Now we have a line. Okay, a line, x-axis. Okay, and they say Q, small q, is placed where x is 0. So when x is 0, there's x0, and where x is 2 meters. Where x is 0 and where x is 2 meters, there's the two charges placed. Where x is 0 meters and where x is 2 meters, Q is here, and this one here is big Q. Okay, so here are the two charges. One is at x equal to 0 and one is at x equal to 2 meters. This charge is called Q, small q, and that one is called capital Q. Now they say if Q is equal to negative 40 picometers, Q is equal to negative 40 picocoulomb, sorry, and big Q is just equal to 30 picocoulomb. Determine the net flux through a spherical surface. Okay, so a spherical surface with a radius of 1 meter. So a spherical surface with a radius of 1 meter. So if it has a radius of 1 meter and it's centered at the origin here, its radius is going to cut the x-axis where x is equal to 1 meter. That's where its radius is going to cut if it's centered at the origin. Okay, so it's going to look something like this. So it's going to look something like that. It's going to make a sphere with a radius of 1 meter, cutting the x-axis at 1 meter. Okay, so that's the kind of sphere. I know that is a horrible line, but it's going to cut the x-axis at 1 meter. Okay, that charge Q. Now they're asking the flux through that surface. So the flux through this particular surface here. Can someone please tell me, okay, what is the charge enclosed by that surface? Can someone tell me what is the charge enclosed by that surface? One of you guys tell me what is the charge enclosed by the surface? Okay. Sibulele, Mr. Sibulele. You can go ahead and tell me. Let me see. Is it in someone write it in the chat or what? Okay, there. Simlindile said negative 40 picocoulombs and someone else has agreed. That is correct. So the charge enclosed by that surface, guys, is indeed negative 40 picocoulombs. That's the charge enclosed, okay? So now we can work out the flux, correct? So once we have the charge enclosed, we can work out the flux, okay? Because the electric flux is equal to the charge enclosed divided by sigma naught. The charge enclosed is negative 40 times 10 to the negative 12 divided by 8,85 times 10 to the negative 12. And that gives us an answer of negative 4.5 Newton meter squared per coulomb. And that is the electric flux through that surface there that we just drew. That's the amount of electric flux through that surface. Okay, and that basically is question number 26. Okay, now question 27 is quite a fun one. Okay, it's the same, it's almost the same as question number 26, but they always like to ask this particular one. By the way, we got negative 4.5 as an answer. Let's just check. And there we have it, negative 4.5. Let's continue. Question number 27 is similar to the one that we did now. It's almost the same one, but they like to ask this particular one. Either there's a multiple choice. Okay. It says a point charge, question 27 says a point charge plus q is located on the x-axis at x equals a. So this is the x-axis. Okay, it's there. That is a terrible. Let's try to make it better. This one's not going to be much better, but yeah, it's a little bit straighter. So this is x, the x-axis. Okay, that is the x-axis. This is x equal to 0. And they say a point charge plus q is located on the x-axis at x is equal to a. Okay, so this is x equal to a. And there at that point is a charge called q. Okay, plus q, plus q. So we don't know what the value of this charge is, we just know it's plus q. Okay, now and then they say, and a second point charge is at negative a. Okay, so right there, same distance in the negative direction, so at negative a there is a charge called negative q. Okay, now a Gaussian surface, okay, with a radius r is equal to 2a is centered at the origin. Okay, what is the flux through the surface? Now they say we have a Gaussian surface with a radius 2a. Okay, this is a, this is 2a, that's 2a, and this is going to be negative 2a. Now a surface with a radius negative 2a is going to cut. It's going to be from radius will be, it's going to be centered at the origin, and its radius is going to be 2a. So it's going to cut the x-axis at 2a and negative 2a. Okay, so this is going to be my Gaussian surface. I know it's going to be a little not too, oh, it's really weird. It does not look like a circle at all, a sphere. But anyway, you get the picture. It's going to cut at negative 2a and at 2a. Okay, can someone please tell me what is going to be the enclosed charge? Can one of you just let me know what is going to be the enclosed charge? Someone just let me know what. Okay, yeah, Simlidile on the money again. He's correct, of course. Anyone else? Hazard a guess. The enclosed charge. How much charge is enclosed in that surface? Remember, this is the surface, okay? From negative 2a to positive 2a, that's the surface. How much charge is enclosed by it? Okay, someone agreed there as well. There's two people. Yep. Yes, you are correct. It is indeed 0 coulomb. Okay, you see the charge enclosed is 0 coulomb. Okay, it's 0 coulomb because you need to add up all the charges enclosed by the surface. Okay, and if you add up negative q and you add it to positive q, it's just going to be 0. Negative q plus positive q, doesn't matter what it is, it's going to be 0. So the enclosed charge is 0, which means the amount of electric flux, just move it up, the amount of electric flux is equal to the charge enclosed divided by sigma naught, which is just going to be 0 divided by sigma naught, which is 0. So the electric flux is 0 Newton meter square per coulomb. Okay, that is the electric flux. Okay, so let's go and check if we are indeed correct. It says, now all of these answers, the first one says A, it's 0 because the negative flux over one hemisphere is equal to the positive flux over the other. That is exactly correct. You see, this one charge is going to bring a positive flux and the other one a negative flux, and they will cancel out. It's not going to be greater than 0. It's 0 every point on the surface. Nope, that's not wrong. That's wrong. The first one is, it is the first one, A. And yes, it can be determined. Which is A. Question number 28. Okay, this is where I'm going to ask some of you. This is our second to last question, I think. We ended 29. 29 is the more involved one. It'll take us about 5 or 10 minutes for 29. But 28 is really fun. I love it. Which one is this? This was 27. No, this is 27. The next one is 28. This one I'm going to do now is question 28. Question 28, and then it's 29. Question 28. Just check the time. Okay, so question 28. We have that drawing there. Okay, there are 4 closed surfaces. Okay, and together with some charges, negative 2q, q, and negative q. Okay, and the colored lines are the intersections of the surfaces with the page. Okay, what is the electric flux through the surface S1 to S4 respectively? Let's start with S1. Okay, S1. Okay, it's the brown surface. Okay, can someone tell me what is the enclosed charge? Okay, remember, we know that the flux is just going to be, the charge enclosed divided by sigma naught. Okay, so what will be the charge enclosed in S1? So it's going to be the charge enclosed divided by sigma naught. Okay, what is the charge enclosed by the surface S1? If someone has a guess, the charge enclosed by the surface S1. Let me try to enlarge it for you guys. There should be better now. The amount of charge, negative q. Okay, negative q. I got negative q. Someone got negative 2q. Mr. Schultz, you can say it out loud. You can switch on your mic if you want to say it out loud. Guys, if you don't want to type, you can say it. The charge enclosed.
I think it's a negative q, so.
Negative q again. Okay, it seems negative q is leading the pack at this point. And yes, you are indeed correct. The amount of charge enclosed by the surface S1 is negative q. Why do I say that? Is because if you add up all the charges inside that surface S1, there is 2 charges in there. It's negative 2q plus a q1, and if you add them up, yes, Simlindile, I see you got it there as well. That's negative q. So the amount of flux through surface 1 is negative q over E naught, or sigma naught. Now let's go to S2. The amount of flux through S2. S2 is the light blue line, the light blue dotted line. Okay, what is the amount of enclosed charge? Again, we are now to S2, the amount of enclosed charge. It's the blue, light blue line. The amount of charge enclosed by that light blue line is guys. Oh yeah, I got an answer there. Yep. Most of you got it right. The amount of charge enclosed by S2 is 0, which means it's going to be 0 flux. S3, same thing. The amount of charge enclosed by S3. S3 is the black line. S3 is the black line. It's got a negative 2Q, plus Q, negative Q. Yes, Simlindile, straight on the money there. Anyone else? Yep, yep. It is. Most of you got it correct. Negative 2Q. Okay, that's the answer, or the amount of charge enclosed by surface number 3. Okay, so the answer is going to be negative 2Q over sigma naught. And finally, S4. While I'm busy writing it down here, how much charge is enclosed by S4? It is the green one. The amount of charge enclosed by S4. Yep. Bali, you are on the money. Anyone else? Yep. Simlindile, also correct. Mr. Caesar, also correct. The answer is 0. There's no charge enclosed by that surface. So it's going to be 0. Now if we stack them in order, S1, S2, S3, S4, the flux is going to be negative Q over epsilon naught. Epsilon, yeah? And then it's going to be, 0. Then it will be negative 2Q over epsilon naught. I said sigma the whole time, sorry, it's epsilon, and then 0 again. Let's see if we have that combination. Negative Q over epsilon, then 0, then negative 2Q, then 0 again. Yep, that's it. The first one right off the bat is the correct one, okay? And yes, that is basically how you work out flux. You find out what surface, how much charge is enclosed by the surface you're working with. Now, question 29 is the real fun one here. Okay, and it's going to take us about 10 minutes and then we're done with the session. Okay, then you get a more or less, then you will be fine going forward with Gauss's law. Now guys, I'm going to tell you something that I told the SI session class yesterday. Please do not get behind in this particular module. Okay, in the first semester you could have gotten by with high school. Oh yes, you will be doing the someone, a similar dealer, just asked, can we apply the same technique to question 29? The answer is no. In this case, we're going to use a different formula for flux. Okay, remember how I originally explained flux as the amount of an electric field going through an area. We're going to use that formula now. Okay, there are two ways to calculate flux. We've done the one, okay, and now we're about to do the other one. Okay. The first one we did to calculate flux, but let me just finish my thought. Please don't try not to get behind in this module, because right after this, when you do Gauss's law, first of all, you need to get a handle on all of your calculus integration. It's going to become standard in this particular module. They're just going to assume that you know the calculus for Gauss's law. The next thing that you need to know is don't get behind, because once you're behind here, it's going to be a struggle to catch up again. Because after this, you have magnetic statics, you have magnetic fields, you have electric fields and magnetic fields, and then they combine those two to create electromagnetism. Okay, you've done already electromagnetic waves, light, and stuff like that, and this is the groundwork leading up to that. Okay, so please try not to get behind in this particular module. Okay, so question number 29. This is where all of this comes molded together nicely. Let me just find out the time. There it is. Okay, so we have two methods of calculating electric flux. Okay, one of them is this one. It says electric flux is equal to the charge enclosed divided by epsilon naught. That is the first way to calculate electric flux. Oh yes, Bali asked, can we apply the techniques they were taught in SI? Yes. Okay, this, and then I'm going to teach that technique as well. The second way to calculate electric flux is equal to this. It's just the perpendicular component of the electric field, and I'm going to teach you how to get it, multiplied by the area that it goes through. Okay, so it's just the electric field, the component of the electric field that is perpendicular to that area. Okay, let's say, what do I mean by the perpendicular component of an electric field? Let's say this is a circle, okay, right? And the electric field, now, obviously, anything that's perpendicular to the electric field must be parallel to that, to this area. Anything parallel to this area anything perpendicular to this area must be parallel to this line here. Okay, this line. It is the area, the parallel line, A parallel, okay? So anything perpendicular to that line is perpendicular to the area, right? Now let's say the electric field is not going straight like that. It's not perpendicular to the area, but it comes in at an angle, say like that. Let's say the electric field comes in like that, okay? That's the angle that the electric field comes in, okay? We are only interested in the component of the electric field that is perpendicular to the area. Does that make sense? We are only interested, when we use this particular formula, we are only interested in the electric field, the perpendicular component of the electric field. The electric field won't always come perpendicular to the area. Let's say this is the area. Now the electric field won't always hit the area perpendicular. Sometimes it might come at an angle from above or from below or from the side. It won't always hit it perpendicular, okay? Now we are only interested in the component of the electric field. Remember, the electric field is a vector, and we are only interested in the component of that electric field that is perpendicular to the area. Okay, does that make sense? Does that make sense, guys? Okay, so Medila says, can I re-explain a bit? Okay, okay. Imagine this. Okay. We have a circle. Imagine this page, right? We're going into the page. Okay, I'm going to take this picture into the page. I'm going to draw this square. This is the area we're working with. This is A. Okay, this is A. Okay, now this dot represents an arrow coming straight out of the page. Okay, now this arrow coming straight out of the page is perpendicular to the page. Does everyone get that? Does everyone, first of all, does everyone understand this part where I just explained that the area, this dot coming out of the page, that is perpendicular to this area, okay? This is the area, this block is the area, and then the point coming out of it, the block out of the page, is perpendicular to it on all sides, okay? It's perpendicular to it, okay? Now, let's say something, the arrow doesn't come out perpendicular, okay? Let's say that is the perpendicular arrow. It is coming like that, perpendicular, nice, at a right angle, okay? That is perpendicular. Now let's say the electric field is not at a right angle. It's coming at this angle here. It's coming at some sort of angle. Okay? It's not perpendicular. Now, in this case, we only ever work with the perpendicular component of the electric field. We only, this is the electric field, and that will be the perpendicular component of that electric field. Okay, remember, it's just perpendicular to the area. We only work with the component of the electric field that is perpendicular to the area. Does that make sense, more or less now? some Lindile. Does that make sense now? Okay, Mr. Caesar says he is cool with it. The definition. Okay, some Lindile says it's fine. I assume everyone else is fine with it as well. We only work with the component of the electric field that is perpendicular to the area. That is all. That is like the crux of the matter. Okay, once you understand that, then you should be fine with the rest of this formula. Okay, we only work with the component of the electric field that is perpendicular to the area. Okay, so it doesn't matter if the area is, say, this page here. Okay, we will only ever work with the component of the electric field that is perpendicular to it. Okay, now Mr. Sibulele asked, what about the parallel component? Okay, in this case, uh, Mr. Sibulele, uh, that is going to be 0, okay? Because when we talk about flux, we talk about the amount of stuff that flows through an area. Now, if it is parallel, it's going to flow right past the area. Okay, does that make sense? Sibulele? Okay, yeah, cool. You see, the reason why we only work with the perpendicular component is we are just calculating the amount of stuff that goes directly into the surface that we're working with, directly into the area or the surface we're working with. Now, if we're talking about parallel, it's just going to slide right past the surface, right? It's not going to flow into it, okay? It'll only flow into the surface or the area if it's parallel, or if it's perpendicular. But if it's parallel, it's going to flow right past the surface, okay? And it's not going to flow through it. Okay, now let's go. We have this situation in number 29. In problem 29, when is it? They say consider a closed triangular box. Okay, so this is a closed triangular box. Yes, it can have different normal spaces. Okay, remember, for instance, let's say the surface is a cube. A cube has 6 faces. Okay, so a cube will have 6 different faces. Okay, and it will only flow into 2 of those faces. Okay, depends. Let's say the electric field is going this way. Okay, it will only flow through the faces that is directly perpendicular. The other faces will be parallel to it, if it makes sense. Let's say this is my phone. Okay, this is the area. Okay, it has a different normal face. Basically it's a prism. Okay, because it's not perpendicularly flat. It has height, width, and length. Okay, now if it flows towards the face of my phone, it's going to flow into my phone, and if the electric face is perpendicular to the face of my phone, it's going to flow in and out the back of my phone. Okay, but it still has a top face, it has a bottom face, it has a side and 2 side faces. It has 6 faces. Okay, but if it flows through the face of my phone, it's going to flow. It's going to be parallel to these 2 faces, the faces on the left and the right, and it's going to be parallel to the top and bottom faces. Okay, that's why we only ever consider faces that are perpendicular. Okay, because if it's flowing parallel to a face, then it's not going to flow through that face. Okay, but yes, the surface can have different normal faces. Does that answer your questions on Sumlindile? Mr. Mzondi? Okay, so you're asking, do we only pay attention to the direction of the field in relation to the face? Yes, not in relation to the field. I assume that's what you meant. We only pay attention to the direction of the field in relation. Yes, we only pay attention to the field in relation to the face. Okay, the surface or area, whatever. Okay, we don't care about. Okay, cool. Okay, so now we have this situation here. We have this situation. Let me just write it. It says consider a closed triangular box. So that is a triangular box there. Okay. It is resting within a horizontal electric magnetic field of 7,8 times 10 to the 4 newtons per coulomb as shown in that figure. What is the electric flux through the entire surface of that box? Okay, let me enlarge that drawing quickly. Okay, so there's the drawing. I'm going to draw every face. Okay, so the electric field is hitting this thing from the back. Okay, now this is what this box looks like from the side. Okay, this is what it looks like from the side. This is exactly what it. Oh, that is terrible. I need more paper quickly. Okay, I've got more paper. I've got more paper. So, I'm going to draw this box from the side. This is the box if we look directly at it from the side. Okay, it's just a triangle. Okay? This is the box if we look directly at it from the side. And that angle there is supposedly 60 degrees. Okay? So, the electric field is from the back. E is from the back. It's hitting it like that. Okay, so that's the electric field. E. And we have the value for E. Okay. Now from the side it is hitting, if we look at it from the side, obviously you already have the side field drawing with L, the electric field coming there. We have the height here is just 10 centimeters. That height from there to there is 10 centimeters. And then it has a length or a breadth of 30 centimeters. Okay, now, first of all, they want the flux through that entire surface. Okay, the flux through the entire surface. Okay, now the flux going through the back surface here, the back surface. Let's calculate that first. There are three surfaces we can calculate. Well, let's call this the back surface. Okay, the flux through the back surface. The area, let's first calculate the back surface. Now the back surface is going to be a rectangle, okay? The back surface, this is for the back surface. The back surface is a rectangle. Rectangular face. The back surface is a rectangular face, okay? And the area for that rectangular face is equal to 10 centimeters multiplied by 30 centimeters. Okay, so it's 10 centimeters multiplied by 30 centimeters, and that is equal to 300 square centimeters. Now we don't work in centimeters, we work in square centimeters, we work in square meters. Now if you convert that, we get 0.03 square meters. Okay, you divide by 1,000. Divide by 1,000.
So shouldn't it be 0.3?
0.3. Wait, let me just check. If you divide by centimeters squared, it's 1 meter. There's how many centimeters? 100 per meter, right? 1 meter has 100 centimeters in it. Square that, you get 10,000. So there should be another 0 there. It shouldn't be 0.00. Can someone just check?
Sorry, sir. Aren't you supposed to first calculate the hypotenuse of the triangle?
No, not at this stage yet, because we are only working with the back part of this triangle. Remember where the electric field is coming in here.
Okay.
We are only, for this part, we're only first working with the back part, where the electric field is coming in at the back there. Picture this as a ramp, we're only working with the back part of the ramp, where it shows the height, that back part there, where the electric field comes in, we are only working with that rectangular surface again, at this moment. Okay?
Oh, okay, sir, I understand, thank you.
Okay, let's just do this. You guys can see the screen there. Okay, we have 300 square centimeters. Of course, you should do this. You can't take the shortcut when you are writing an exam. You should know how to convert this 003. So yes, 300 square centimeters is 0.03 square meters. Okay. Yep. Yeah. So, yes, we have the area now. I worked out the area. Now, remember the formula for electric flux. It is equal to the perpendicular component of the electric field multiplied by the area. Now I'm going to ask a question, okay? When you look at that back surface here, okay, is this electric field hitting this surface at the back here? Remember, we're only dealing with this part of the surface, this back surface here, that I just darkened here, okay? Is it hitting it perpendicular? Is the electric field hitting that surface perpendicular? Can you guys tell me? Is it hitting that surface perpendicular? Who said yes? If you say yes, then please. Oh, Simlindile says yes. If you say yes, just give me a thumbs up if you think he's hitting it perpendicular. Okay, Bali says, she says yes. Mr. Cole says yes. Okay, everyone else, most people say yes. That is correct. This electric field here is hitting the back surface, although they don't expressly tell us, but it is hitting it. Let me just check it. Do they tell us? No. Horizontal electric field. So the electric field is horizontal to the ground, so it is hitting it. Yes, it is hitting it perpendicular. So we don't need to calculate the perpendicular component of this electric field because it's already hitting the back. Remember, we're only dealing with the back side now. It's hitting the back at exactly 90 degrees. So we calculate what's the electric field then? It is given to us as 7,8 0 times 10 to the 4 newtons per coulomb multiplied by the area of 0.03 square meters, and there we have our electric flux. If you see this here, that's the units for electric field and that's the units for area. Check out what the units are going to be for the electric flux: Newton meters squared per coulomb, and that's exactly the units that we got for our previous formula. Okay, so it does work out. If you calculate it mathematically, it should be. Now this is something that I always kilonewton. Okay, it's kilonewton, so it's going to be 2 times 3, 2,340 basically. Okay, here's the thing though. Usually, this formula, I'm going to write it here. We don't write it this way, E perpendicular. We just write the electric field, whatever is given, multiplied by the cos of theta. Because if you want a horizontal component or the perpendicular component, we use the cos multiplied by the area. Okay, in this case, I'm going to leave that negative there. It's going to be negative, but I'm going to show you why it is negative in this case. In this case, we are measuring the incident angle, the cos. It is measured from that point there, going that way. So it's 180. And it does get a little. Remember, in this case, I know it hits the surface at 90 degrees. Yes, that is true. Okay, but what is its relation to the perpendicular of that surface? The electric field is parallel to the area of that thing. It is perpendicular to the surface itself. But remember, the surface or the area itself has a line that is perpendicular, that is perpendicular to it. Now, theta is the relationship between this area, this area is, you see this dark line that I'm drawing here now, that is the line that is perpendicular to the surface. Now you want the angle between that line and the electric field. They are going parallel to each other, but in opposite directions, so it is 180 degrees, okay? The distance, well, the angle between the electric field, which is going this way, and the area of, this is the area, the perpendicular vector of the area, and then this is the perpendicular component of the electric field, and the angle between them is 180 degrees. It sounds a bit weird now, but over time you'll get used to it. Okay, so cos of 180 is just going to give us this negative sign. That's all it does. Okay, so let's continue. We've worked out the electric flux for the back area. Let's work it out for the slanted area, that ramp part of it. But first, let's work out the surface area for that slanted piece. Okay, before I go on, is everyone with me so far? I know it sounds a bit weird. This part will explain where the theta is. Theta is the angle between the perpendicular of the area, not the perpendicular vector from the area and the electric field. That is theta. Theta is that angle. Okay, so let's see, understood. Anyone else have any problems with it? It's just the angle between the vector that is perpendicular to the area. Remember, the area can be a vector. Okay, it is the vector between the area and then the vector, the electric field vector itself. That is theta. That is theta. Okay, and that's the angle that we always use with those two angles. Okay, most of you understand. Okay, so going next, now we've worked out for the back part of the surface. Now we've worked out for the back part, now we're going to do it for the slanted side. It's this ramp part here that I'm coloring in here. Now we're working it out for that particular part there. This part here, we're working it out for that part. Now, that part has a perpendicular area vector going that way. Okay, its perpendicular area vector is there. Okay. So, let's see. There's a perpendicular area vector there. Going out there. And we have an electric field going that way. Remember, the electric field is perpendicular, so it's all coming out here, perpendicular to that area. That's the electric field coming out. Okay. Now, theta is the angle there. There is theta. It is that angle there. Now what can that angle be? Okay, remember that one goes there. It is perpendicular to the area. That's the area vector. Okay. Now the electric field is going there. It's coming out here. Electric field is going there, coming out there. That is a brilliant take on it. Guys, Leela just wrote a brilliant understanding of it, and I never thought about it that way. You see, I'm smart enough to admit when I'm meeting someone that has an incredible intellect. Okay? Simply Leela says you should think about it as friction and the direction an object moves in. They will always be in the opposite directions. Okay? The reason why the angle between them will be 180 is just because we know that friction is in the opposite direction. It's just going to give friction in a negative direction. Okay? So, that is a good way to think about it. If you read your chat, you'll see Cinderella says the following. It's the same thing as friction in mechanics when an object moves in a different direction, while friction always goes the other direction. For those who didn't understand, it says in this case the normal of the object is moving in a different direction to the electric field, resulting in a 180 angle. That's a brilliant take on it, Lindile. Okay. And that's a very cool snake you have on your profile there. Judging by the head, it's some sort of viper, no, a constrictor. I used to study zoology. Oh, anyway, some sort of constrictor python. Okay. Now, let's go to the next part. We're doing the slanted angle now. We want this angle here. Remember, that is theta. It's the angle between the electric field going straight out of the field and the perpendicular area vector. Now, the area vector is always perpendicular to the area. That's the area. It's slanted. Now, the area vector is this big black arrow that I drew here very roughly. Now, we want this angle here, theta, that I just drew in there. Now, this angle here, let's just check something. This angle is 60 here in this corner. This one is 90, which means this one here will be 30. Okay? And the angle here, if that one is 30, remember this whole thing here is 90, so this one will be 60. Does everyone agree with me? This one will be 60. This angle here will be 60, meaning theta is also going to be 60. Does everyone agree? Can you guys just did you guys understand why theta in this case is going to be 60? Can I just give, okay, Sianda, if you have a question, you can ask. You raise your hand, you can ask. I'm just explaining why. Okay, just ask the questions, guys. You can either type it or just switch on your mics if you can. I'm going to stop for a moment there and then ask whatever question you may have. But while you guys are getting ready to ask the question, I'm going to redraw it on a different page. This is the we're dealing with the slanted face now. Okay, that is the area vector. Okay, it is always perpendicular to the area. That vector there is the area vector. Now we always deal with the angle between this vector and the electric field itself. Why pick a point? Oh, I could have picked any point, anywhere. Okay, I just picked it somewhere where it is easy to see. I could have picked it here. It will be the same thing. It will give you the same answer. As long as it's perpendicular to this area here, it doesn't matter where I pick the... Let me just throw this one up here. Okay, I'm going to draw that situation again. This is the slanted area, right? Oh, that is too slanted. This is the slanted area. Okay, let's draw it here. Okay, that is the area vector that is perpendicular to the surface, this slanted surface. Okay, that is the area, the perpendicular to the area. It's 90 degrees to the area. Always, it can be in the midpoint, it can be at the end. Does that answer your question, Similila? Okay, why as to why between the midpoint? I didn't have to be the word midpoint, I just drew it there for symmetry reasons. Okay. Okay, so this is the vector that is perpendicular to... Now we have the electric field is going here right through. It's going right through this box. Okay, that's the electric field. Now we are always dealing with the angle between this vector that is perpendicular to the area and the electric field. That is theta. Okay, so we want theta here. This is theta. Okay, we want that value. We know that this value here is 60 degrees. Okay, we've been told that angle there is 60 degrees. We know that this thing is perpendicular here, so that thing is 90 there. In that corner it's 90, which means at this corner here, right here, it's 30 degrees. Okay, it's 30 degrees. Let me draw it here. There's the area vector. Okay. There we have the electric field going that way. We want that area there, theta. Okay. So, but we know that the area here is 60. That is 60. Now if we just finish this up, This one here is 90. It will be here 30 degrees. Okay, it will be 30 there. This one is also going to be 30. Okay, now if we just extend that, it means this one is going to be 30 and 30. This is going to be 60 degrees. Does that make sense? Which means the angle opposite it is going to be 60 as well. This one is 60, and since this line is always going to be 90 degrees, okay, it will always, the area vector is always 90. It means the sum of the angles on this line here, on this side, will always be 90. Now we've already established that that one is going to be 30 degrees because that is 60 and that is 30. Okay. Now if that one is 30, that one is 60, then the angle directly opposite is the Euclidean geometry is going to be 60. So theta is 60 degrees. Okay. Now let's continue. Okay, let's first work out the area of the slanted angle. We are doing the slanted face. The slanted face. Its area is equal to, let's work out the area. Oh, but here we have something, we don't have the length of, we first need the length of that slanted. Can someone suggest a way to get the length of that slanted face? We don't have the length, we don't have that length there. But we have that length and we have that angle. We will basically just use our old geometry. Okay, yep. In this case, Pythagoras is correct, but we'll be using sine cosines because we have one length. Remember, we have this length here. We have this length here, it's 10. We have that length there, it's 10 centimeters. And we have that angle there, it's 60 degrees. That's all we need. The sine of 60 is going to be this angle here over that. No, the cosine of 60 is going to be that angle 10 over that length x. Yep, trig functions. Mr. Mbewana, there, said it. Trig functions, the area, we want that first, but we know that the cos of 60 degrees, okay, there's the angle there. We want the length of that slanted line there, okay? And the cos of 60 degrees is going to be, let me just, where is it? The cos of 60 degrees is going to be 10 centimeters divided by the hypotenuse there, which is, let's call it x. Therefore, if you just work it out, it's just going to be, x is going to be 10 divided by the cos of 60. X is going to be 10 centimeters divided by the cos of 60 degrees, and it is equal to 10 divided by the cos of 60 is 20 centimeters. So we have 20 centimeters. That slanted line has a length of 20 centimeters here. So we have it 20 centimeter length, and then we have 30 centimeters in breadth. Okay. So the area of the slanted line, slant, is equal to 20 centimeters multiplied by 30 centimeters, which will give us an area of 3 times 2 is 6, and that is 600 square centimeters. And if we work it out, it goes to about 0.06 cubic meters. So now we have the area of the slanted side. We know that electric field is equal, remember we originally worked out, the original electric field we worked out was, just keep that in mind, negative 2.3 kilonewton, negative 2.34 kilonewtons, okay? So now the electric flux is equal to E multiplied by the cos of theta multiplied by the area. Okay, now the electric field in this case is equal to 7,80 times 10 to the 4 newtons per coulomb multiplied by the cos of 60 degrees multiplied by the area, which is 0.06 square meters, and that gives us an answer of 2.34 kilonewton meters squared. So it's exactly opposite to what we got here. Here we got negative, and here we got the same answer but positive. Okay, so we worked out for two surfaces now. We've worked it out for the back and the slanted surface. Now I'm going to ask you guys a question. Okay, what's going to be the electric field, the electric flux through the surface on the side? Okay, this triangular surface here, the one that I'm coloring in now, this surface here, what's going to be the electric field in that surface? Let's see how many of you can have paid attention. What's going to be the electric field through that thing there? Remember, we only ever deal with a surface. Zero. Okay. Avuile, can you tell me why you say zero? Simple word. Just one word. The electric field. We always work. Okay. Anyone tell me it is zero? The electric field through all the other surfaces are going to be zero. Why? Yes, yes, yes. Brilliant, Avuile. Brilliant. The reason why for all of the surfaces, the triangular surface on this side, the triangular surface on the other side, and the bottom surface are all going to be zero because of one simple reason. All of those surfaces or all of those faces are parallel to the electric field. They are parallel, meaning the cos will be zero. No, the cos will not be zero. Yeah, cos will be zero. Cos will be 90. So it's going to be, anyway, they are parallel, meaning the electric field will not flow through it, so there will be no flux through it. Okay, they are parallel. Okay, meaning now they ask us for the total. Remember, they originally asked us for the total flux. Okay, now the total flux, total electric flux, total is going to be that original one we got of 2.34 kilonewtons per meter squared per coulomb plus 2.34 kilonewtons meter squared per coulomb plus for one of the sides, one of the triangular sides. Yes, it's because the angle is 90. And then for the other triangular side and for the bottom, it's all going to be 0. And that gives us an answer of 0. 0.
Sorry, sir.
Yes, Seppo?
So is it true that for an enclosed surface, meaning like a shape, a cube,
Yes,
or whatever shape that we may have,
yes.
always the flux will be equal to 0?
For an enclosed surface.
Yes, sir.
No, it won't. It'll only ever be 0 if that surface is parallel to the electric field, meaning the face of that surface is parallel to the electric field. Or in other words, if the angle between the electric field and the area vector of that surface is 90 degrees, because the cos of 90 is going to give you 0. Let me give you an example quickly. Let's say I'm going to draw the bottom part of that triangle, right? It's just the part that's on the ground. That is it, right? Do you agree?
Yes, sir.
Okay, now the area vector for that thing is going to be this. For that face is going to be pointing downwards like this. Okay. Now the electric field is going this way. The electric field, that's the electric field. It's going that way. Okay. It's going that way, parallel to the face itself. But the angle between the electric field and this angle here is always theta. Must remember where that is theta. Okay, that's theta. That angle. Now this angle will start here and it's going this way, and that is exactly 270 degrees. Okay, and the cos, now that is theta. That is theta. If you work it out, the cos of 270 degrees is equal to 0. And that is why there will be no flux there. And you can picture it this way. None of this electric field is actually flowing through the surface. Remember, flux is just a measure of how much the electric field flows through a surface, okay, or a face or an area. Since this area is parallel to the electric field, none of that electric field lines will actually go downwards. It's just going straight over it. It's flowing over it. None of it is going through that surface. Does that make sense?
Yes, it does.
Okay, the same thing works for the sides. Let's say this is one of the sides, rather not the bottom. That is one of the sides. Same argument. the electric field is just going to flow past it. None of it is going to flow through it. Okay. Now, that is when it's parallel. When the angle between the area vector and the electric field is equal to 0, the cos of that angle, that cos of that theta is equal to 0, then, or in other case, that face is parallel to the electric field. No matter the way the field is flowing, it's going to be parallel. But the other part of your question is, you asked if the surface is enclosed, okay, the flux will be 0 when there is no charge inside. Remember that old formula of ours, which says the flux is just equal to the charge enclosed over E naught. If it's, remember, so far we've dealt with surfaces that have a charge enclosed by charges, that enclosed charges, and we've done surfaces in which an electric field just flows through. Okay? They are both the same thing. The reason why I say the same thing, because every charge, any charge that is enclosed, like for this formula, the charge enclosed creates an electric field that flows through the surface. That's it.
Okay, so if there's a charge inside the shape,
Then the electric
flux-
field, the flux will be non-zero. Or it depends on the charge. If the total charge inside, if you sum up all the charges in the surface and it's 0, the flux will always be 0. Doesn't matter what is the shape, it can be any safe shape you can imagine. But if the charges inside adds up to 0, the flux will always be 0 because of this formula here.
Okay.
Okay.
Thank you, sir.
Okay. And that, guys, is the end of our session for today. If there are any other questions, please ask me now. If not, then enjoy the rest of your public holiday, especially you ladies. It's your day. That's it from me today. Hope to see you next week. Semlindila, you have a question? You raise your hand. You can ask. Oh, you don't have one. I just saw your hand raised. Mr. Caesar, your hand is also.
So I wanted to ask, in terms of the area vector, so we won't be considering it if, just say the electric field was moving, the electric field was moving perpendicular, like it was coming out and it's perpendicular to the surface, but it's not, the electric field is not going towards, it's coming out of the surface, but it's perpendicular. So would that mean we will have area vector cos 90?
Let me teach you something that you used to think of this, but you haven't thought about. You used to know. You actually know this. Let's say we have this surface and we have a charge here. It's creating an electric field, and this electric field is, obviously, it's positive. It's a positive charge, and it's creating an electric field going outwards like that. Okay, it's creating an electric field going outwards like that. Here's the fun thing, though. Okay, it'll hit this thing at 90 degrees. It'll hit it at 90 degrees. Now the area vector, this is the electric field. Okay, it's going to hit the surface of the charge at 90 degrees. The area vector for this surface is here. At that point, at that exact point there, the area vector at every point there is also going to be at 90 degrees. So the area vector, here I'm going to draw it longer, the area vector is also in the same direction. So the cos between these two, the angle between them is 0, and the cos of 0 is equal to 90 degrees. The cos of theta, or the cos of 0 degrees, is equal to 1. The cos of 0 is 1. So, yes, you will be able to answer that thing. I don't know if I answered your question. Can you just restate the question?
Oh no, you answered it because I was wondering why we didn't consider the area vector when the electric field was going out.
Oh yeah, in most cases, you will find you can consider it. It works for the reason why I use the example of a circle is because it's when it hits the surface of that thing, it's going to be 90 degrees. But In some cases, it won't always be 90 degrees. Okay, for instance, say a square, if it's in the middle there, it's in the middle, it might hit that point there at an angle, but then you don't use that formula of course and stuff. You won't use this formula, you just calculate the amount of charge inside. When you're dealing with charges and you want to calculate flux, when you're dealing with charges, here's the golden rule of this whole thing. If you're dealing with charges and you want to calculate flux, just, and this is Gauss's law in its simplest form, you will be using this formula. The charge enclosed divided by sigma naught. That will give you your flux. That's it. You will use this thing, this formula. If there are charges involved, you use this formula. So the minute you see they have this amount of charges there, this amount of charges, you use this formula. But the minute they give you an electric field, you use this formula, E naught cos theta times the area. If the minute they give you the electric field, you use this formula. The minute they give you charges, you use this formula. One day you will understand that these two are exactly the same formula, just different variations of it. So, if you are dealing with charges, if they give you the charges, you use this formula. If they give you areas and angles, or most importantly, if they give you the electric field, you use this formula. But if they give you charges, they use this formula. Those are the two formulas you need to know to calculate flux. And you will be using them interchangeably as long as you're comfortable with both of them. But the next demi, which is tomorrow, Arnold will be doing a lot more problems on this. So I was just doing the introduction. Does that answer your question?
Yes, thank you.
Okay, that's cool. Now, guys, I have to say adios. Our session is done. Enjoy the rest of your day. Thank you for listening on a public holiday. Much appreciated. Bye, guys.